My name is Sophia Cibei, and today I will be presenting my thesis entitled Freight Rail Electrification Optimization. So freight rail is one of the most sustainable forms of freight transportation, producing 16 times less carbon pollution than freight road. However, almost all freight rail, particularly in Australia, is powered by diesel. And as industries move to decarbonize, this reliance on fossil fuels becomes a very big liability. And therefore, industries are looking for alternative solutions to power our freight rail. And that is where battery electric freight rail comes in. However, just like your Teslas, battery electric freight rail must be charged along its journey. We need to create infrastructure along its route to allow the batteries to be charged or to be swapped. But how exactly do we do this in a feasible way? So this is basically the crux of my thesis. And in order to answer this question of how do we create these stations in a feasible way, two things must be done. We first need to determine the energy required by the train to traverse along a particular route. So an energy consumption must be modeled. And then from that energy consumption model, we can provide that energy in an optimal way. So in order to develop this energy consumption model for my thesis, I analyzed three main energy consumption models currently in the literature. So these three main ones were the ones that I thoroughly looked at. The first two, all of them use the modified Davis equation, which is an equation that is, I guess, foundational for all energy consumption for trains. The first train looks at diesel trains and is validated on US data, and the second model uses an electric train and is also validated on US data. The third model, however, is slightly different. It does look at electric freight rail, but once again is validated against US freight data. So in my literature review, all these models were relatively accurate. Looking upon them, all the errors range from about, it was just under 1-ish%, which was quite good. And as I said before, they all use a modified version of the Davis equation, as you can see here, which I will touch on a little bit further as I introduce my energy consumption model. However, although we have three relatively good energy consumption models, there is a gap in the literature, particularly when it comes to Australian freight electrification of rail. So the first thing, there is a lack of freight-specific battery electric modeling. The first two models didn't look at freight-specific rail. It looked at passenger trains, which has different energy consumption demands compared to freight rail. The third one, however, did look at electric freight rail. However, it used this customized throttle parameter, which limits its applicability to all different types of trains. That's an input that's quite difficult to find for every single train. Secondly, there is very limited literature when it comes to focusing on how do we create charging infrastructure for battery electric freight trains. There seemed to be very, very little literature on that at all. And then finally, there were no energy consumption models that were tailored for Australian freight routes. And as one of the papers that I did read, variations in climate can really change the energy consumption demands of a train. So having a model that is tailored for Australian freight routes is really important, and that's something that we hope to close the gap on. So what does my thesis hope to contribute? Well, first and foremost, I hope to contribute a battery electric freight-specific energy consumption model. And with the output of this model, it will then be passed into an optimization algorithm that Dr. Jia Guo has created. With these two models built, so my energy consumption model and the optimization model, they will be combined into, or they have been, I should say, they have been combined into a tool to help guide practical infrastructure planning and inform decision-making for charging and swapping of batteries. Then my thesis looks at a case study demonstrating feasibility on a real Australian corridor, being the corridor from Sydney to Dubbo, which Transport for New South Wales, Marek, a few months ago, so very kindly gave us the data for to help me do a case study for my thesis. So in order to develop my energy consumption model, I had to look at what did the current literature have and what additional things could I create for this model. So everything highlighted in yellow here is the unique input parameters for my model. So not all of the energy consumption models incorporated regenerative energy from braking for electric freight rail. And they also didn't take into consideration the maximum acceleration and deceleration of a train, which will vary from train to train. And they also did not take into account max tractive force. So these are 3 input parameters that are unique to my model. The rest, however, is built off of these 3 other energy consumption models. Okay, so basically this is my energy consumption model, which draws on a lot of the literature, and then later you'll see my unique input. So the first equation we have here is the modified Davis equation. Essentially, this equation takes into account the mass of the train, the frontal area of the train, so air resistance on the train, the mass on each axle, and then it also takes into consideration the resistance that comes from the grade of the track and also the curvature of the track. So the vertical grade and then the horizontal curvature. With that resistance, those resistance forces calculated, the tractive forces can then be calculated. So how much force does the train need to exert to overcome these resistance forces and then also traverse at the required speed? Then we get tractive power, and then finally, I guess basic physics, we find the energy consumption, and then here we also have regenerative power from braking that has been generated. As you can see here, this formula was drawn on model 3, and that was combined with all the other models to produce my energy consumption model. So the unique aspect of my model is that almost all the data that we receive around the train and how it traverses is in a function of distance. You know, at a particular distance or chainage on a route, this is the speed limit, this is the grade, and this is the curvature. But if you can see here, all of the, particularly the resistance forces, are a function of time. So my model looks at converting these functions of distance to a function of time. And in order to do that, we must need to calculate the acceleration, and then from the acceleration, we can find the velocity of the train. So this is kind of the logic of my model. The first thing, iteratively, so every single time step, the train first looks at how much longer, or what's the distance until I need to stop at a particular station. And based on the maximum deceleration that the user has inputted, we can see, based on the speed that the train is going at, and based on the maximum deceleration provided by the user, what is the required stopping distance to stop at a particular station? So we have the stopping distance, and from there we go on to this next flowchart, where basically iteratively we have a look at, does the train need to start braking, or can we start accelerating or cruising at this particular speed? And iteratively through there, we can calculate the acceleration, or if it needs to, or deceleration, if it needs to brake at a particular station, or if, however, it can just cruise and accelerate based on the maximum tractive force and the mass of the train. We can rearrange Newton's second law and find the acceleration of the train at a particular instance of time. So here is a summary of how I've converted the functions of space, particularly the speed limits, the grade, the curvature, from functions of distance to functions of time. And also how I've used velocity to convert distance as a function of time. So if we have the time, we can figure out the distance that the train is along the route, and then from there, we can convert the functions of speed limit, grade, curvature from functions of distance to functions of time. So with my thesis, I did 2 case studies where I tried to compare how accurate my model was to validated energy consumption models that we saw in the literature review. So in case 1, or case study 1, I looked at a flat, straight route that goes for about 5 kilometers. And these were the input values that I provided for my model, as well as it was model 1 that I compared this to, which is called a train sim. The highlighted values in yellow are the input parameters that are unique to my model. So the other model didn't take in this input. It was input that was solely for my model. And here you can see the changes and their associated speed limits. And as I said before, there was no curvature and no slope in this particular case study. In this case study, we can see that my model projected that the train required 452-ish kilowatt hours of energy to traverse along this particular route, whereas the energy consumption calculated from model 1 was slightly less. It was 337 kilowatt hours. So the difference is quite a little bit for this particular case study. We can see the difference is about 34% with my model calculating that more energy is required than model 1's calculations. Sorry, there's a bit of a typo. That should say case study 2. But in case study 2, we have very similar, I think the train characteristics that I provided for this case study are the exact same as case 1. So as I've gone over before. But in this case, the route that it traverses is the same distance. However, there is a grade and there is curvature on this particular case study. Now, what was very exciting was my model calculated that the train would require about 715 kilowatt hours to traverse this particular route. And the model 1 calculated very similar amounts of energy, about 707 kilowatt hours, with only a 1% difference between my model and their model, which was quite exciting. So in summary, both models act in the way that we would expect. With more grade and more curvature, more energy is required for the train to traverse that particular route. But there is some difference between the model that I have developed and the results of model 1, particularly in case 1. There was about 34% difference, but very similar results for case study 2. And these would be attributed to my unique contribution from my thesis. So that would be how I calculate acceleration and velocity, and how I take into account the maximum attractive force that the train can exert on the rails. We don't really know what model 1 does to calculate the acceleration and velocity of the train along the route. So that's probably where they arise. However, this was a hypothetical route with a hypothetical train. So unless we have further real-world data, we can neither validate nor invalidate my model. So I guess further steps from here would just be more information, more real-world data on the routes and the types of trains that would be traversing these particular routes. Now with my energy consumption model explained, I will join you shortly again, but I will pass you over to Jia Guo to discuss how she came up with her optimization algorithm for the feasibility of charging stations.
Okay, thank you, Sophia. Now I'm going to discuss the model. Before we dig into details, I would like to show you the motivations of our model. As we know, the battery electric trains can replace traditional diesel trains to transport goods from their origin to destination. This will create zero carbon emission, which is very, very sustainable friendly and environmentally friendly. However, one problem is a battery can only support the train to travel a certain distance. After that, the battery has to be either charged or swapped. And therefore, we need to decide to set up several charging or swapping stations along the route from the origin to the destination. When we are deciding the location and the number of stations along the route, one of our goals is to minimize the infrastructure setup cost. After the stations have already been set up, we also want to make efficient use of energy and charging time by providing a good charging and swapping schedule. Therefore, we can summarize two objective terms from the motivations. First, we want to minimize the total station setup cost. Second, we want to minimize the total delay due to charging or swapping. Then I'm going to show you the operational mechanism of the station. Suppose the train will start from the origin and drive along the route and all the way to the destination. And there are several potential locations where we can establish the station. Let's say we have locations 1, 2, 3, and 4. Suppose we decide to deploy station 2. Station 2 can be used to charge or swap batteries. And here's how station 2 operates. The train, which carries one or multiple batteries, starts from the origin, and it arrives at station 2, which is already deployed. When the train has arrived at station 2, the SOC is already very low. By saying SOC, I mean the state of charge, which is the percentage of energy in the battery. So SOC is always a value between 0% and 100%. 0% means the battery is totally depleted. 100% means the battery is fully charged. When the train has arrived at station 2, the state of charge is already very low. Then it has 3 options, and the train has to choose exactly one from the 3 options. In option 1, it can choose to charge one or several batteries. By the end of that, the charged batteries will have higher SOC. Remember, we don't need to charge all the batteries to 100%. In the second option, we can swap one or several batteries. By the end of that, the swapped batteries will have SOC of 100%. Option 3, we choose to do nothing. Then, when we leave the station, the SOC are unchanged for all batteries. When we have chosen the option and used the option, the train can leave the station and head to the destination. Okay, then we can summarize our decision variables from the operational mechanism. We have 3 groups of variables. First, we need to decide whether to deploy a potential station or not. Second, for each train, we need to decide the number of consists carrying batteries. We make this value a variable because we know the capacity of the train is really limited. If we assign too many batteries to a train, there won't be enough space for cargoes. The third decision is on charge swap scheduling. That means when a train has arrived at the station, we need to choose whether to charge batteries, swap batteries, or do nothing in that station. If we choose to charge the batteries, we need to decide when to start charging the battery and to what state of charge a battery when the train leaves the station. If we choose to swap batteries of the train, then we need to decide the swapping start time of each battery. Okay, then we have constraints. Basically, we have 3 groups of constraints. First, we need to make sure the charge stations must provide sufficient power for the trains to travel from origin to the destination. Second, we have requirement on the minimum carrying capacity of each train to ensure there's enough space for cargoes. Finally, we consider the capacity of each charge station. That means we include an upper limit on the number of chargers and an upper limit on the number of fully charged batteries. Finally, I'm going to show you the assumptions we'll take into account. Most of the assumptions have already been discussed in the section of operational mechanism. I'm just going to emphasize the first 2. The first assumption means charging a battery takes much longer than swapping a battery. For example, swapping a battery might just take 2 hours. However, charging a battery from 0% SOC to 100% SOC might take up to 10 hours. The good thing is the user can always adjust those parameter values from the user face developed by Sophia. Our second assumption is the charging speed is never a constant. It varies based on the remaining power in the battery. This can be reflected from our daily life. Suppose we're charging our cell phone. The charge speed is usually very high when the SOC is low. For example, if the SOC of our phone is only 5%, then it might just take a few minutes to charge it from 5% to 30%. However, if the SOC is already like 95%, then it might take really long to reach 100%. It is the same case as the batteries on the trains. Therefore, the charging speed is not always a constant. It can change based on the remaining power in the battery. Next, I'm going to give time to Sophia. Sophia will discuss her case study and show her fabulous user interface.
Yeah, I'm back. So to incorporate my energy consumption model and Jia's optimization algorithm, we wanted to do this on a real world, real Australian corridor. And as I said before, Transport for New South Wales so kindly gave us data, real world data on the speed limits, the grades and the curvature from Sydney all the way through to Dubbo. So in this case study, we are imagining that we have a financial budget of $100 million. So I guess you could think of it like, okay, let's construct charging stations along this route to support electric freight rail, but we only want to spend $100 million. Obviously, it'd probably be a bit more than that, but just for simplicity. And we're also going to say that we don't want to delay these trains along the route when they're charging by more than 100 hours. Now, I will have to say that these values can be changed however you like in this model. These were just some nice round numbers that we decided to go with. And we also put weighting towards these two budgets. So I guess for us, time is a bit more important. So we gave it a weighting of 0.05 and the financial budget a weighting of 0.01. Once again, these can be changed. So if you're really rich and you just want something really instantly, you can say I'll spend as much money as I like and put much less weighting on finances than time, or you can do it the other way around. If you don't have too much money and you want to save and you're happy to wait. So in this case, I have come up with these are made up stations. These are made up stations along real chainages, but with made up fixed setup costs, made up maximum charging of batteries at these stations, and also made up maximum swapping capacities of these charging stations. So as you can see here, we've got our origin, which would be central, and then our destination, which would be Dubbo. And then we have in between 14 different stations that the algorithm could choose to select for charging of this electric train. And here you have just a map of Sydney to Dubbo. You don't know where it is. So for this particular case study, these were the train characteristics that were provided into my model to figure out the energy consumption of this particular train. So these results show that once the route characteristics of the speed limit, the grade, the curvature, and the train characteristics were inputted into my model outputted a matrix of the required energy from every single station pair from origin to destination, and also a matrix of the time from every single station pair. With that output, that was then given into Jia's model to select the most optimal charging station locations, but also for the sake of showing how good this optimization algorithm is, we also ran a worst case scenario, because this could potentially happen if you don't have any optimization model, you had someone just plan these stations however they like. Worst case scenario is that they pick the least optimal stations to be built and to charge these stations, to charge these trains. So for the worst case scenario, you would be spending with these with this route and these train characteristics in this budget, $99.1 million, and you will have a delay of 4.67 hours. That is because you will be deploying 4 stations along the route, and those setup costs will be added to 99.1 million. And however you decided to charge or swap these batteries, it will delay the journey by 4.67 hours. If, however, you had used great optimization model, instead of spending $99.1 million, you would be spending $39 million and only be delayed in terms of time by 2.89 hours, because only one, so that should be, I think that's the type on my end, I'm sorry, that should be 2 stations are deployed in this particular instance. So the difference would be in terms of cost, you're saving about 60%, which is really, really big. And in terms of time, you are saving, there's a difference of 38-ish%. And you are halving the number of stations that you have to deploy if you use this optimization algorithm. So this is a little bit of a visual. I will run you through my tool and show you how it works. But in the worst case scenario here, you should be able to see the purple line is the route that the train takes to go from Sydney to Dubbo. And all those little icons of like a train looking thing is the potential charging stations that could have been picked for this route. The green icons are the stations that were selected to be deployed for this train. So in the worst case scenario, you can see that there are about 4 dots. So 4 stations were deployed. On the other hand, in our best case scenario, you only see 2 green dots. So only 2 stations were deployed, and therefore that's why the setup costs were much less. And however, whatever they chose to do at those stations, minimize the time delay. So in conclusion, the developed energy consumption model does vary slightly, with the case study 1 showing that there were slight variations, and then case study 2 showing really similar results to model 1. And those differences arise from the variations in acceleration and velocity that I have contributed to. Also, in conclusion, we can see that the algorithm does a really good job of reducing cost and reducing time delay. As I said before, a 60-ish% reduction in cost and a 38% reduction in time delay. But as I said before, we require some more real-world data to further validate my model or calibrate it correctly, and then also further show the feasibility of this optimization algorithm. We do have time because I'm not time constrained, so I have to show it from here, don't I? I will run you through what it would be like to use my tool. So just another summary of what the tool is. This is a user interface where I would say it's quite simple and easy to use. The user will just have to import train characteristics for that electric freight route, input the route characteristics through an Excel file, which again is very quick and easy, and then also input the potential charging stations that they would like to select. Then they just need to press a button. It will run this optimization, firstly, the energy consumption model, show a matrix of the energy consumption and the time delay. Then they press another button, and then that will show what would be the recommended action at each station, which station should be deployed, and should the trains be charged or swapped. Must the batteries of the trains be charged or swapped? And then it also outputs this in a nice visual way on a map. So I'll run that using this tool, run through that with you. Okay. So here you can see I've inputted all the data for this particular train. I might just stop here. So previously here, I've just inputted the power of each locomotive, the mass of the locomotives and the cars, and all these other parameters that are required for my energy consumption model. Once that's done, you can come over here and input your data for the route. So here I'm putting in the Sydney to Dubbo route information, and I'm also inputting the possible stations that we could select along this route. So here you can see all their, that started from the beginning. I'll let it do its thing. So here you'll see all the different chainages that could be where the different stations could be, or the chainages corresponding to those. And then here also you have the maximum amount of batteries that can be charged simultaneously and the maximum number of batteries that can be swapped simultaneously. Here I'm generating the energy matrix for this particular route with these provided potential stations. So you'll just go to a different tab and you will see all the different energy consumptions in terms of batteries to go from the start or origin station to the destination station. And here you also have the time matrix, so how long it takes to go from every single station pair. So with that done, those outputs are fed into Jia's optimization algorithm model. And we pass the output of the optimization model here. So I just want to pause here. So here you can see a table that summarizes everything that is recommended to be done at each potential station. So station 1, we're not deploying it, so therefore we do nothing. You can see here all the different stations you can pick from, their corresponding chainages, the time that they arrive at those stations, and the time that they depart those stations. And then if they're charged or swapped, if the batteries are charged or swapped, there will be a delay. But as you can see here, none of the stations are deployed. So there is no delay. We see here if the station should be deployed or not. And then for each of the batteries on the train, we can see the action at each station, but also the arrival state of charge and the departure state of charge. So this table summarizes all the different actions for every single station along this route. So as you can see here, for the optimal case, station 7 is recommended to be deployed, and they're recommending that you swap 3 of the batteries, and then you continue along the route. And then I think in this particular case that I went through, no other stations were deployed. This isn't the same case study as the one I've introduced earlier. So then what you can do is input the start and end coordinates of your train stations. So here we've got our starting station, which you can see the icon being Sydney, and then the destination station being Dubbo, and you'll see as I zoom out a little flag to show that this is the destination station. And then we run more code to show the possible routes that could be taken, and then the route that is taken, the possible charging stations to be selected, and then finally the charging station that is selected. So as you go along the purple line, you can see that's the route the train will take. The different icons here are all the potential stations you could pick, but the green circle is the location of the station that is recommended to be deployed. And as you hover over each of these stations, it will tell you more information. So station 7 we knew is deployed. Oh, I'm sorry. Let me go here. So here we can see that station 7 is at this particular chainage. The train arrives at 3.6-ish hours, and then there is a delay of 2 hours because the batteries are being swapped. So then it departs the station after 5.66 hours. So we can also hover and get more information about that train. I think this just shows it in a nice way, not just in a table format. Yeah, that's my tool. That was my presentation.
Okay, great. Presentation. Let's see if there's any room, any question in the room, and also from online. Let's just right. Let me just check the chat box. Right. Any question in the room? Yes, Mion, go ahead.
Well done, both of you. I think I might have missed the equations of the energy consumption.
Sure.
Were they load dependent or were they only mass dependent of the cars and the?
So I'll get up the equations. It's slide 10. Slide 10.
Yes, this one.
So the question was, are the calculations load dependent or mass dependent? Could you clarify what you mean by load?
Load of the train's empty or if the train has something that's carrying.
So I guess that would also be mass. So with the input on my tool, the user would, I guess, change those loads, or, you know, if it's empty, this is what the mass would be. If it's loaded, this is what the mass would be. So it would be up to the user to provide that updated mass for the train.
Load
Yes. Which, now that you bring that up, that could be something that could be changed.
No, it's actually same.
It's named? Oh, okay.
That depends on the route.
Depends on the route.
So
Yeah.
they usually go from Sydney all the way to Double and then empty and Double and then come back. Is that how they usually do it? Or that's a
But again, the user can actually change it for the user interface. But yeah, for this case study, yes, we consider the fixed route, fixed load for that route. Yes.
Stack or
For my particular thesis, because I have limited scope, yes, I'm just looking at my train, but I think later on, Jia had already incorporated that into her algorithm, but for the sake of my thesis, I just focused on one train, one route.
So one thing, for freight services, we don't really have that much frequency. It's not like passenger trains. And for that particular route, the route or the path is shared between passenger and freight. But passenger actually, we didn't consider the passenger train charging, because actually they can use overhead wiring for charging. But not for, actually they do that now already.
a big question for Jia. The energy consumption model, do you have to linear? Is it that's not necessarily linear, is it? Or is it is? You incorporate it into your optimization. Did you have to do any linearization of the energy consumption model or no, you did not?
This energy consumption model, we just generate the amount of energy required between every two nodes. So they are just parameters.
I see. So I see. Okay. So so the optimization looks for the optimal number based on a pool of possible solutions. That's how you did it, or?
Not really. We don't have a pool of potential solutions. We just suppose we don't have anything, and then we need to generate a solution from the model. For example, we need to decide whether to build that, whether to set up that station or not, whether to have the train charge in that station or not.
As a parameter of the model. Very good.
Thank you. Presentation. So we are on this slide. There is a regenerative power of braking part. Is it just specific to the electrical system, or we can have it for the diesel fuel? For diesel fuel, can we have that regenerative power? Or
Not for diesel, no.
do you know? And did you compare the energy consumption for fuel type and electrical type?
No, so for my particular thesis, it was focusing on how do we select the charging stations optimally. It wasn't really comparing, and I think there's a question here in the chat, which I'll talk about. The focus of the thesis wasn't on diesel versus electric freight rail. However, if that is required from someone, I can do that. The other models did look at diesel energy consumptions, and one of the tools that I used to compare my model to existing models does have the ability to look at diesel fuel. So if that is something that we want to explore further, that's definitely something that I can do and compare to show that perhaps using the regenerative energy for electrical freight rail, we use less energy, and therefore not only can we select stations more optimally, we can also use less energy, and therefore it's more sustainable.
Yeah, that's why I'm asking the question. First, I was wondering how much the weight of regenerative power in the whole equation. I was wondering if that makes difference, so much difference between electrical system and that's, I mean, if the difference is huge, then using the electrical system would make sense. Otherwise, they would go with that diesel type.
But what about decarbonization?
Oh, that's a good question. Actually, if the difference is low, then we go, for example, assigning some penalties on CO2 emissions. But still, I think if the difference is not very high, that penalty would justify. I mean, although you would have that penalty, you still would go with the diesel type.
Yeah, so in this study, we basically assume that we want to electrify. And then we have two options, either battery swapping or charging. And we have some potential sites that we are exploring which one of those, considering the energy consumption for that particular route, would be feasible and would be more cost effective if we have the charging. So the research questions was a bit different from like comparing.
Did you have any charging solutions? So I looked into your solutions, they were mostly about swap. Did you have a charging station as well as solutions?
Yeah, so for that particular example that I showed you, I think station 7 was selected and 3 batteries were recommended to be swapped. But it really varies. You can swap them or you can charge them. It depends on what Jia's algorithm recommends.
And the last question about the weighting system, how did because the summation wasn't equal to 1. So what would be why did you choose, for example, 0.01 and 0.5? How did you come up with those weighting systems?
So for those particular, I'll hand it over to Jia to explain that a bit more. But for that 0.01, waiting for, I think it was financial cost,
Yes.
and 0.05 waiting for time delay, those were just selected. It was made up. We assumed, like a lot of the data here around the stations, fixed setup costs, it was all just data that I. Oh, okay. So basically, if you weight it more, basically you're saying that that is more important to you because the idea is to minimize that optimization.
Yeah, but in the weighting system, we usually go with the weights that their summation equals 1.
Yes.
Yeah.
Yes. So usually the weight so we have two terms, right? So usually the term, for example, for delay is alpha, then the other one is 1 minus alpha. How do we decide alpha? Usually we try to transfer, for example, delay to amount of money, amount of cost from the delay.
That makes sense.
And that can be compared with the setup cost.
Questions and Michael from DP World. So Michael also asked, are you going to compare with the base example of a diesel locomotive today, as we need to compare between liters of diesel to kilowatt hour for a business model? And I think you kind of partially answered that already.
Yeah, that was a similar question. Just asking the audience. Sorry, I just realized you probably can't hear the question. So very similar question was around, did we compare diesel versus electric freight rail? And my answer was, for the focus of my thesis, no, it was around how do we optimally select charging station for an electric freight rail. So we assume that electrification is the better way to go. However, as I did say, there was a tool that I used that can provide me with the energy consumption for diesel, a diesel freight rail. So if that is something that you would like, I can't do it today, but that can be done in the future. I can compare the energy consumption in terms of kilowatts for the electric train, and then we can look at the energy consumptions in terms of liters of diesel for the diesel powered freight train. So today, no, that wasn't the focus of my thesis, but that is definitely something that can be easily done in future.
Yeah, one of the really good things that I really liked about your work, Jia and Sophia, particularly Sophia, for the tool that you developed, is a flexibility that you give it to user. And I remember that, Marek, if you are still on the call, your recommended route was from Sydney to Parks. However, now with this user interface, you actually can plug it in any route that you may actually have the whole new SAT-wall. So the tool actually will work for any route.
Yep.
So basically, you just need the chainage and the curvature and the gradient of that route for
And speed
any and speed limit as a like an Excel spreadsheet, and then you just embed it,
Yeah.
plug it in to the user interface, and then even the user can change some of the parameters that Jia has in her model. For example, if you think that battery swapping doesn't really need 2 hours, it could be done in 1 hour, you just change that 1 hour. Or about the cost and all of those things. So basically, that's a very flexible tool that government and anyone actually can just play with it, and then you can run the model. The only thing that you need is basically the correct logic and the algorithms that are robust, and actually we validated them both in terms of the energy consumption, validated them against the peer-reviewed literature in US that Sophia did, and also in terms of the optimization. The work actually is already under the review of a journal as well. So is there any question? Mike, I see that your video is on. Would you like to add anything?
Okay, yeah, no, thanks for the credit at the top. Yeah, no, I look forward to correlating this more with and I haven't spoken to locomotive manufacturers myself, and it is top call at our end for our purposes. So yeah, I believe I recognise the tool that you've created and how we can play with the parameters to make it applicable to my task. But yeah, it's goes a long way to proving the viability of such a an operation, and looking forward to collaborating further, if I may.
Yes. Okay, that would be lovely. Yes.
Cheers.
Okay, great. Thank you. If there's no more question in the room, thanks for joining us. And yeah, just consider also tuning in for the next RC seminar. But please also put your hands together for very outstanding work by Sophia and Jia. I'm very proud of you, Sophia. Jia, but Sophia, seriously, you're just undergrad. It was just honest research project, but honestly, like you went above and beyond my expectation. So I'm very proud of you, and the best of luck for your next career.
Yes.
Hopefully we'll have you again soon for PhD. So yeah, let's put your hands together for. Right, thank you so much. Yeah, so let me just stop the recording. And thanks everyone.
Thank you, everyone. Thank you for tuning in.